Welcome to section 14.3. In this section, we're going to be looking at the concept of taking derivatives of functions of two variables or more, and that is the idea of partial derivatives. So when we compute derivatives back in Calc 1 and Calc 2, we are taking the derivative of y with respect to x, so the derivative of f of x with respect to x. But now that we're in functions of two variables, we can't take the derivative of f with respect to its only one variable. We have a choice now. And we can't take the derivative of both x and y. What we can do is take them one at a time. So we can take the derivative of f with respect to x, or we can take the derivative of f with respect to y. And this is why they're called partial derivatives, because you're taking the derivative of that whole function with respect to part of its variables. So the partial derivative of f with respect to x at a point AB is denoted fx of AB. So we have a little subscript x down here. So this is not f times x. This should be like just slightly below the f and smaller. So fx is how we read that. Fx of AB. This is the partial derivative of f with respect to x. And in order to do this, we let y be fixed. And we'll talk more about that in a little bit. The partial derivative of f with respect to y at AB is denoted fy of AB. And we let x be fixed to compute this. So in terms of their formal definition, taking the limit definition of the partial derivatives, so we get fx of xy is the limit as h approaches 0 of f of x plus h comma y minus f of x comma y all over h. And similarly for fy. So you can see in these formulas, they do very closely mirror the Calc 1 limit of the difference quotient that we use to define the derivative. But of course, the function has two variables, but we're only working with one variable at a time. So we can see here for the partial with respect to x, we let x be the one that changes and y stays the same. And then for fy, we let y be the one that changes and x stays the same. Okay. Now, luckily for us, we're not going to be spending a lot of time working with limits of difference quotients in here. We're going to dive right into the differentiation rules and notation and all that kind of stuff. The good news is the way that you compute derivatives does not change in these partial derivative functions. There's just a couple small adjustments that we have to make kind of mentally. And if we can make those adjustments, then these go really smoothly. So a little bit of notation to start us off. So we saw, fx of xy, fy of xy. These often get abbreviated fx and fy, okay, with the subscript there. We had the Leibniz notation back in Calc 1. There is an equivalent notation instead of dy dx. So it would be like partial z with respect to x and partial z with respect to y. So notice this symbol is not the letter d. It's not dz dx like that. This notation, this is a partial derivative symbol. Okay, so it's partial z with respect to x and partial z with respect to y. Very important to keep that notation straight because it implies that there's more than one variable. This can also be written partial f with respect to x, partial f with respect to y. So if you're trying to draw it, the best suggestion I would give is it's kind of like a backwards 6. Now, with the function here, we can also write partial with respect to x of f of xy and partial with respect to y of f of xy, like that. Or lastly, sometimes you can see capital D sub x of f and capital D sub y of f. We won't really be seeing those a lot in here, but they can come up. So now when it comes to actually computing these, if we take a look at the diagram that I have over here on the right, let me zoom in on that. What we're doing in taking a partial derivative is we're looking at the same point in question, so that's the point ABC up here, if you will. In Calc 1, there was only one direction to go. You had your curve, and so we picked the point, we drew the tangent line, and the slope of that line was the derivative. But in 3D, you don't just go one direction. You don't go left to right. So we have to single out a couple of specific directions to take the slope in, and that's what these partials are. So we can see here I've got my surface, I've got the x direction and the y direction here. So right, the direction of the x-axis, direction of the y-axis. And if we project those up onto the surface here, you can see the green. So this is kind of like its shadow. It's running along the x direction, or excuse me, the y direction. And the purple one is running in the x direction this way. If we draw tangent lines at that point in those specific directions, we will get different slopes. Okay, so like T1 here, that's going in the x direction. You see how like its shadow is this purple curve. And then this one, T2, is in the y direction. You can see how its shadow is that green curve right here. So you'll get different slopes in different directions. Now, where we're heading in the long term is we want to be able to get the slope or the derivative in any direction, not just the directions of x and y. But to do that, we need the slopes in x and y directions. So the rule for finding partial derivatives of z: to find fx, regard y as a constant and differentiate f of xy with respect to x. To find fy, regard x as a constant and differentiate f of xy with respect to y. What this means is, as we're going through these problems, if you want to find the partial derivative with respect to x, pretend that y is not a variable. Pretend that y is like a number, okay, a scalar or a constant, because we're holding it fixed. So pretend that y is just a number, and then take the derivative of this function with respect to x as you normally would in Calc 1. Okay, so this is what I mean when I say that the derivative rules are not changing. The way you take a derivative is the same as it was before. The mental kind of hurdle that we have to get over is being able to treat a variable as if it was a number. Okay, and then same thing for fy. We're letting x be constant, so we're fixing x. We're pretending that x is a numerical value, so a constant, and we're taking the derivative only with respect to y. Okay, so when we take the partial derivatives, we're really just taking a derivative one variable at a time, okay, and essentially ignoring the other one. So let's take a look at an example, see how this looks. So we have our polynomial. We want to find fx and fy and evaluate them at the point 2, 1. So fx of xy. Okay, so x is the variable, y is a constant. So if we go first term, derivative of x cubed is 3x squared. No problem there. Derivative of x squared y cubed. With respect to x, x is the variable, y is a constant. So when you have the derivative of, so say this was x squared like times 5, something like that, we treat the y cubed exactly as we would treat the 5. Treat it as if it was a number. So when we take the derivative of x squared, the number would just tag along, right? We would have 5 times x squared. We would do the power rule, bring down the 2, subtract 1, etc., etc., and the number would just stay there. It just tags along for the ride. So that's exactly what the y cubed is going to do. So we're going to take the derivative of the x, and the y cubed just tags along. Okay, so that's the derivative of this term with respect to x. And then this term, minus 2y squared, well, this term has no x's in it. It only has a 2 and a y squared, and y is being treated like a number, like a constant, which means that this whole thing is constant when we're talking about x. So the derivative of a constant is 0. So the derivative of 2y squared is 0. So then for fy of xy, we're going to do the same thing, but this time y is the variable and x is the constant. So x cubed's derivative with respect to y is nothing because it's constant, right? It's no variable at all. Over here, x squared y cubed. Now we'll take the derivative of the y cubed and let the x squared tag along as the constant multiple. So we're going to get 3x squared y squared. And then this one, now we differentiate normally, so that's minus 4y. And now that we have the formulas, we can go ahead and sub in these values. And I'll just tell you this one is 16. And this one is 8. So what this tells us is on this surface, on this polynomial surface in 3D, if you locate the point 2, 1 on the surface, and you look in the x direction, the slope of that surface is 16. So it's very steep in that direction. If you look at the same point, but then turn in the direction of y, the slope is going to be only 8. So it's going to be half of what the slope is in the x direction. Okay. So we get 2 different numerical values, 2 different slopes in 2 different directions. So this would be, for example, like t1 up here, and this would be like t2 up here. Okay, so those would be the slopes of those tangent lines. So this is how we compute partial derivatives. So like I said, it takes practice, but if you can kind of get yourself over this mental jump of treating variables like constants, then we're not really doing anything that different from what you did in Calc 1. Next up, we have a function f of xy, another polynomial, and we're going to find a couple partial derivatives. So fx of xy, derivative of 4 is nothing. Derivative of negative x squared with respect to x, we get negative 2x. And then derivative of 2y squared with respect to x is nothing. It's constant. So fx of 1, 1 is negative 2 times 1, so negative 2. Fy of xy, 0 minus 0 minus 4y. Again, constant. So we get fy of 1, 1. Sub that in, we get negative 4. So again, if we find this function, locate the point 1, 1 on it, the slope in the x direction is negative 2, the slope in the y direction is negative 4. If we introduce a little bit of trig into the mix here, we will need to use the chain rule on this one. So these partial derivatives can make our lives a bit easier because when you have x's times y's, you don't have to use product rule. X over y, you don't have to use quotient rule. Unfortunately, the rules still apply when you're differentiating with like the same variables. So all these rules will still be a factor. And in this one, the chain rule is very much at play. So if we go ahead and take, so partial f with respect to x, we're going to take the derivative of the outside function first, so that's cosine, leave the inside alone, times the partial derivative with respect to x of the inside. So that's x over 1 plus y. So this is the chain rule, right? Derivative of the outside times derivative of the inside, except this time it's the partial derivative of the inside. And the partial derivative here, x is a variable, 1 plus y is a constant. So again, this is just tacked on here. The x is the only part that we really care about, and the derivative of x is 1. The 1 plus y in the denominator, again, constant, it doesn't change anything. So this is going to be cosine of x over 1 plus y times 1 over 1 plus y. Okay. Or you could just put the whole thing over 1 plus y if you want to just combine it into one term. That's totally fine too. For partial f with respect to y, we'll again take the derivative of the outside function. So that is, again, cosine of x over 1 plus y times partial with respect to y of x over 1 plus y. Now this one's not quite as straightforward because we're differentiating with respect to y. So x is a constant, but y is in the bottom of the fraction. So we need to rewrite this a little bit. So we're going to take partial with respect to y. This is x times 1 plus y to the negative 1. All right, so make a negative 1 power, and now do the power rule. So that's negative x 1 plus y to the negative 2. And then when we move that back down, that'll give us our final form of this. So that's going to be negative x over 1 plus y squared. And that would be our partial derivative. For the next example here, we have some implicit differentiation. So like I said, the idea of the partial derivative does give us some help in simplifying derivatives without doing like products and quotients and all that stuff. However, implicit differentiation is still a thing. So if we're going to find partial z with respect to x, z is defined implicitly as a function of x and y. So z is still the output, x and y are still inputs here. So we need to take the partial derivative with respect to x of all of these terms. If it's an x, it's a variable. If it's a y, it's a constant. And if it's a z, it is a function of x. So we will take its derivative and then apply the chain rule, okay, to get that partial of the inside also. So let's go term by term here. So that's going to be 3x squared plus 0 plus 3z squared times the partial of z with respect to x. Okay, and actually I'm going to move this over because this line gets a little bit longer. Okay, so again, that's the implicit differentiation because z is a function of x. So we took the derivative of the outer part, that was the power part, times the derivative of the inner part. Okay. Plus, now the derivative of this. With respect to x, we have a variable here and here because z is written in terms of x. So we do have to use the product rule in this case. But 6 and y are just going to tag along for the ride the whole way. So we get derivative of the first times the second plus derivative of the second times the first. So we're going to get 6yz. So we took the derivative of the x, which was 1, plus 6xy. We took the derivative of the z, which is 1. But we do have to include partial z with respect to x because we differentiated the z. equals derivative of 1 is nothing. Now, our goal is to solve for these. So I'm going to subtract off everything that does not have that in it. So we're going to get 3z squared partial z with respect to x plus 6xy partial z with respect to x equals negative 3x squared minus 6yz. Then we're going to factor this common term out. So partial z with respect to x. And this should, at this point, I know it's probably been a while since you've done implicit differentiation, but if you go back and look at some problems from like Calc 1, you should see that this mirrors that process very closely, just with partial derivatives instead of whole single variable derivatives. And now we divide both sides by this piece to isolate the partial derivative. So we get partial z with respect to x is negative 3x squared minus 6yz over 3z squared plus 6xy. And this would be fine. You can also simplify this a little bit. There's a common factor of 3 in everything. And we could even just take the negative out of these two and put it out in the front. So like negative x squared plus 2yz all over z squared plus 2xy. Something like this. Again, the other one was fine too, but that's kind of our fully simplified version of that derivative. Next up, we have the concept of higher derivatives. So we can take derivatives of higher orders. So just like in Calc 1, if you take a derivative, you can also take a derivative of that, right, to get the second derivative. And then the third derivative, fourth derivative, et cetera, et cetera, et cetera. Same thing here. It's just that you can take partial derivatives and you have to indicate which variable you're taking the partials with. So if f is a function of two variables, its partial derivatives are also functions of two variables, so we can consider their partial derivatives. So that would be if we take fx and take its partial with respect to x, you could take fx and take its partial with respect to y. You could take fy, take its partial with respect to x, or you could take fy and take its partial with respect to y. And these are called the second partial derivatives of f. So notationally, we have a few different ways of writing this. Of course, the one that we just wrote up here, but oftentimes we don't like to put the parentheses around this every single time. So we'll just condense it. So this would be fxx, fxy, fyx, and fyy. Then we could also apply the partial notation, so like that Leibniz notation. We could take the partial with respect to x of partial f respect to x. We could take partial with respect to y of partial f respect to x. Partial with respect to x of partial f respect to y. Partial with respect to y of partial f respect to y. So you can see the ones inside here. That's the first one. That's fx, fy, fy. And then we take the partial of that with respect to x or y for the second. Now, in terms of the notation, if we want to condense this one, this is where it gets a little bit trickier. So for the first one, it's no problem. So we get partial squared f respect to x squared. Same thing for y. So we get partial squared f respect to y squared. The issue comes when we get to these middle two. because they work kind of almost counterintuitively. What happens is we don't go in order like we do with these two. We basically just get rid of these parentheses and just smash them together in this form, which means that this y is going to come before the x. And when I say before, I just mean to the left. So this is going to be partial squared f respect to y respect to x. And this one is going to be partial squared f respect to x respect to y. But this one has x first, then y, and it goes right to left. So partial x, then y. And again, it's because of this notation here, where we're just smashing these two together, and the partial x was on the right, so it stays on the right. Okay, so we just got to be a little careful with that. But other than that, it behaves again the same way. And you can also use z. So partial squared z respect to x squared, etc. Right. When it comes to computing these partial derivatives, it's not anything different. It's just more of the same thing. So it says find the second partial derivatives of this function. We already found the first partial derivatives, right? That was the work we did earlier. So we got 3x squared plus 2xy cubed for fx. And for fy, we got 3x squared y squared minus 4y. So for the second partial derivatives, there's going to be 4 of them. So it's going to be fxx of xy, fxy of x and y, fyx of x and y, and fyy of x and y. So for fxx, we take fx, so this one, and now take its partial derivative with respect to x again. So with respect to x, we're going to get 6x plus, with respect to x, that becomes a 1, and the 2y cubed just tags along. So we get just plus 2y cubed. fxy, so we go again to fx. Now take its partial with respect to y. So that's a 0. This, we bring down the 3 and subtract, so we get just 6xy squared. Then over here, fyx, so now we're moving on to fy, and we're going to take its partial derivative with respect to x now. So let's see, we're going to bring down this 2, so that's 6xy squared tags along, and then plus 0, so that's done. And fyy, so again, we take fy, partial again with respect to y, we bring that down, that's 6x squared y minus 4. And these would be our 4 second-order partial derivatives for this function. Now, the natural question that comes up after we do this example is, what about these two? They're the same thing. The question is that just a coincidence, or is that a pattern? Is that something that will continue to happen or not? And the answer is that it is actually a pattern. So this is called Clairaut's theorem. Clairaut's theorem says if fxy and fyx are both continuous, then fxy at AB is equal to fyx at AB. So this is really nice for us because that means that as long as the functions are continuous and their second-order partials are continuous, the order of partial differentiation will not matter. fxy, fyx, they will be the same thing. We can also define partial derivatives of order 3 or higher. Okay, so like for this one, fxxy, for example, But you can take as many partial derivatives as you want or need. And using Clairaut's theorem, this makes this process a little bit easier. It can be shown that f x x y, or excuse me, x y y, well, fxy can be switched to fyx. So this will be fyxy. And then the partial of that with respect to xy can be switched again. So this is fyyx. So it turns out you can pretty much move the order of partial differentiation around to any order that suits us, assuming continuity. And this can help us possibly avoid maybe more complicated partial derivatives if we're taking the partial of something that's really, really ugly with respect to x, but it's really nice with respect to y. We can go ahead and switch it and then deal with the x afterwards, when maybe it's not as complicated if we've simplified it or something. So Clairaut's theorem can be very useful to us. So let's take a look at an example. So we've got a little bit of trig coming in here. Calculate f x x y z for this function. So this is the fourth derivative with respect to x, then y, then z. Okay, so we're going to take four partial derivatives here. So we're going to go step by step. So we've got a function of three variables here with respect to x. So we've got cosine of 3x plus yz times the partial with respect to x of the inside function, because of the chain rule. And that's just a 3 here and nothing here, because y and z are just constants. So that's fx. For fxx, take partial of this with respect to x again. So let's see, the 3 will still be there. We're going to get negative sign. So let me actually put the negative in front here. Sine of 3x plus yz. And then we take the partial derivative of this inner function again with respect to x, which just produces another 3. So I'm going to go ahead and just combine that here. 3 times 3 is 9. Now we're going to take the partial derivative of this with respect to y. So the sign differentiates as cosine, so that's the same. So cosine of 3x plus yz. But now the partial derivative of this part, the 3x will be a 0 because there's no y's in it at all. This one, the y becomes a 1, and so we're just left with a z. So the whole partial derivative of this inside is just z. So I'll go ahead and put that out in front here. So negative 9z. And now we take the partial derivative of that with respect to z, which means now we've got a little more work because there's a z out here and a z in here. So we do have to use the product rule in this case. So we're going to have the first times derivative of the second plus second times derivative of the first. So we'll get negative 9z derivative of the cosine. Excuse me, I said derivative of the first times the second. So we took the derivative of the z, it was 1. So we're just left with the negative 9 and the cosine. Plus derivative of the second times the first. So we still have a negative 9z for now. Times the derivative of cosine is negative sine. So the negative is going to make it positive. So it's going to be 9z sine of 3x plus yz. Partial with respect to z gives us a 0 plus y times 1. So just y. So we'll just add that up in here. 9yz. And so this would be our partial derivative with respect to x, then y, then z. So this is a fourth order partial derivative for a function of 3 variables. So as you can see, we can step this up to much higher levels. A lot of the times we're going to be sticking with functions of 2 variables, taking just first and second order partial derivatives, but it can apply at any level. Now, the last little thing to talk about here is the idea of a partial differential equation. A differential equation is just an equation that has a derivative in it. So a partial differential equation is an equation that has a partial derivative in it. We abbreviate these PDEs. One example is something called Laplace's equation. This says that if you have a function u in terms of x and y, the second derivative of u with respect to x twice, plus second derivative of u with respect to y twice, when added, equals 0. Now, we're not going to be like deriving and coming up with PDEs in here. We just want to see if we can show that a given function is a solution to a PDE, not try to find the solutions ourselves. That would be for a differential equations class. But for this one, show that this function is a solution of Laplace's equation. So in other words, we need to show that this function fits this relationship. So if we just take the appropriate partial derivatives, we'll see if it equals 0 when we add them. And if it does, then it's a solution. And if it doesn't work, then we probably did something wrong because it says to show that it's a solution. So let's go ahead and take a look here. So partial u with respect to x of this. Derivative of e to the x is e to the x. Sine of y is a constant with respect to x, so it's going to stay the same. So that's good. Partial squared u respect to x squared. Derivative again with respect to x, again does not change. E to the x stays the same. Sine of y is a constant multiple. Right? Partial u with respect to y. This will become e to the x tags along cosine of y. Partial squared u respect to y squared. Derivative of cosine is negative sine, so we get negative e to the x sine of y. And you might be able to see where this is going. Partial squared u respect to x squared plus partial squared u respect to y squared. That is e to the x sine of y plus negative e to the x sine of y, which are opposites, so they add to 0. So it does satisfy that relationship from Laplace's equation. So we can say, thus, u of xy is a solution of Laplace's equation. So again, we're not going to be coming up with solutions. We would just be like verifying that a given function is a solution using the techniques of partial derivatives that we have just learned in this section. We're going to be using partial derivatives all throughout the chapter and all throughout the entire course, but this is just our first introduction to them, and that is the end of section 14.3. So when we come back in future sections, we'll be starting to use the partial derivatives to look at some applications, to look at further techniques, and look at more types of derivatives that we can take. And we will cover all of that stuff in the rest of the chapter coming up soon.